Most people talk about AI through the lens of Nvidia, GPUs, CUDA, and data centers full of H100s. That is only half the story. There is a second world of silicon that almost never appears in headlines, yet it trains and serves some of the biggest AI models ever built. These are Google's TPUs, Tensor Processing Units, and they were designed with a very specific purpose in mind: make matrix maths run at blistering speed with as little waste as possible. Google built the first TPU in 2015 because its own internal models were hitting a wall. Running everything on GPUs or CPUs was too slow, too power-hungry, and too expensive at Google's scale. So they created a chip that did one thing exceptionally well: multiply and add numbers in huge grids, the core operation behind every neural network. That is why the word tensor is in the name. Almost the entire chip is designed around this single mathematical pattern. A GPU is a generalist. It can do graphics, it can do parallel maths, and it is flexible enough for almost anything. A TPU is a specialist. It sacrifices flexibility to maximize throughput. Think of it like comparing a Swiss Army knife to an industrial machine built to stamp one shape 10 billion times a second. If your workload matches the machine, it is unbeatable. One of the clever moves Google made was designing TPUs alongside its software stack. The XLA compiler, JAX, TensorFlow, and the TPU architecture all developed together, meaning the software speaks the chip's native language. Nvidia's power comes from CUDA. Google's power comes from controlling the entire pipeline, from the data center floor to the high-level code a researcher writes. The biggest advantage of TPUs is scale. Google builds them into pods, clusters of hundreds or thousands of chips connected with extremely fast interconnects. A single pod acts like one giant accelerator. That makes them ideal for training frontier-scale models where communication bottlenecks matter as much as raw compute. Training a trillion-parameter model is no longer just a question of flops. It is a question of how fast thousands of chips can talk to each other without stalling the entire system. Then comes cost. Google claims TPUs deliver better performance per watt and per pound spent than equivalent GPU clusters for certain workloads. If you can shave even 10% off the cost of running these models at Google scale, you are saving tens of millions a year. When the next generation of TPUs rolls out, performance usually jumps by multiples rather than increments. One of the reasons you rarely hear about TPUs is simple. Google keeps most of them for itself. Anthropic, for example, trains on Google TPUs and has repeatedly said they prefer them for some of the largest model runs. If you look closely at the economics of the large AI labs, there is a quiet split forming. Nvidia dominates the open market. Google dominates its own internal universe, and the company's big enough to partner with it. The interesting question is what this means for the future. If TPUs continue to scale in pod size, communication speed, and software tightness, Google can double down on a fully vertically integrated AI stack. That becomes a deep moat. Nvidia cannot control the data center end-to-end. Google can. Whether that advantage becomes dominant depends on how quickly other players adopt alternatives like AMD MI300, custom silicon, and future optical or analog accelerators. But right now, TPUs represent a different philosophy of AI compute. They are not designed for everyone. They are designed for the giants. If GPUs are the backbone of the AI boom, TPUs are the hidden engine room powering some of the biggest breakthroughs you never see. If you found this useful, you know what to do. Subscribe, give it a like, and check out the merch and Patreon. It keeps this channel independent and helps future projects happen faster.